Okay, let me go back and take a look at just some main ideas from the sections in chapter 3 so far. Okay, first off, the big idea of chapter 2 was all about limits and learning what kind of algebraic techniques and all could help you to determine the limit of things. Okay, the big idea in chapter 3 is that the derivative of a function is really just the limit as h approaches 0 of f of x plus h minus f of x over h. Okay. And that is really just the slope of the tangent line to whatever the function is, to the curve at x, okay? All right, so that's the big idea of chapter 3, is that the derivative is really just the slope of the tangent line to the curve at x in general, okay? Then you know how to do limits, and you know that this right here is the difference quotient. So you had a little bit of review and some work with that. And so we're just putting those ideas together and working on developing the idea of the derivative. Okay, now the derivative doesn't start to be defined that way exactly. So let me just go ahead and look at a couple things. So in 3.1, the big idea in 3.1 was the slope of the tangent line to some curve. Get my pen. At a particular point, the slope of a tangent line, sorry, my pen, I've explained before, I just am too cheap to go buy a new one. They cost a lot. So the slope of the tangent line at x equal a is the way 3.1 starts off talking about it. And there's two basic definitions. The slope of the tangent line, both of them involve limits, can be thought of as the limit as x approaches a of f of x minus f of a over x minus a. Okay, or the one that involves the difference quotient, you can think of it as, so the slope of the tangent line can be thought of as the limit as x approaches h of f wait, I said that wrong. I meant as h approaches 0. Sorry, I'm switching gears here. So instead of doing the one that's as x approaches a, we could have the limit as h approaches 0, and we could do this. It starts out this way in 3.1, okay? Now, if you compare these two, okay, the only difference is you see the a there instead of the h. What's going on is we're looking for the slope of the tangent line at a point. So this would have been an x plus h minus f of x, but they were putting in a particular value. Now that we know more than we did at the start of chapter 3, most of the time when I'm doing questions that involve finding the derivative at a point or finding the slope of the tangent line at a point or instantaneous rate of change at some point, I usually get the formula first and then I plug in the value that I'm looking for. Okay. All right, so these are equivalent formulas. They're just slightly different looking. So let's go ahead and let me pull some problems out of homework. Okay, I'm going to look at problem 9 from 3.1. I want to do some with the various types of functions so that you get used to the algebraic process there. Okay, so with number 9, you are asked to find, okay, this is number 9. You are asked to use the definition, this one here, use this, and to get the slope of the tangent line to the graph at point P. And they gave you the function was f of x equals 3 over x, so that's a rational function, and the point they gave you was the point -3, -1, okay? All right, and they wanted us to use this formula here for that one. And then once we do that, we're supposed to go on and get the equation. So A, we do the slope of the tangent line. B, we get the equation of the tangent line. And then C, they wanted us to graph F and its tangent line. Okay, so that's what we're doing. So this is the slope of the tangent line. This is the equation of the tangent line, and then we're going to graph them. All right. All right, so we're using that first formula for this one. So we're just going to go in and we're going to think about going ahead, since they told us, they told us that this is the point. So this is my A, this is my f of A. See, this is the -3 is my A, and notice if I plug in -3, I get -1 for the y coordinate. So in 3-1, it starts out that you're always doing the slope at a particular point. You're not doing the general formula, okay? So what you would do is you would come up here and you would say, okay, so I'm going to, the slope of the tangent line to the curve at that point would be the limit as x approaches -3 of 3 over x minus f of A would be -1, okay, over x minus the A itself, which is -3. This formula right here is really the y2 minus y1 over x2 minus x1, basically. Okay. All right, so we're going to go on and just work on the algebra involved here. So we're going to do some simplifying. So that's 3 over x plus 1. The denominator is x plus 3. Okay. Now this turns out right here to be a complex fraction. So something I use a lot when I'm dealing with a complex fraction is I use the fact that there's a denominator of x in this case. That's the only denominator. And so if I wanted to clear that out of there, I could multiply everywhere from x by x, top and bottom. So if I multiply by x everywhere, I'd wind up with that simplifying to be 3 plus x over x squared plus 3x. Okay, still need to do the limit of that. Hope you're doing okay with my faulty pen as x approaches -3. All right, so the problem is if we plug in -3 right now, we'd have a denominator of 0. And so it looks like, okay, we're stuck, we can't do the limit. So what we're going to notice is that that denominator can be factored. In fact, I should have left it factored. If you really think about it, I should have just multiplied the denominator by x and left it as an x. But anyway, since I didn't, I'm going to refactor it. So that's x plus 3 down there. Up here, I have 3 plus x. Now be careful. Sometimes when things are out of order, it matters, but both 3 and x are positive, so these really are the same. So those would cancel out. And as long as you weren't right at -3, which we're not, we're just looking for x getting close to it, then the limit as x approaches -3 of basically 1 over x, we can now do because we've eliminated that spot where it was undefined, and it would equal -1/3. Now we can plug in and we'll get it to be negative 1/3. Okay. All right, so that's working with a rational function. Okay. You wind up, I just wanted to remind you of this right here. You're dealing with a complex fraction, and this is one way to simplify a complex fraction that I use a lot. All right, now don't lose track of what you're doing. We've done part A. This is A, the slope of the tangent line. Okay, now for part B, all we have to do is take that slope of the tangent line that we just found, which is the negative 1/3, take it together with the point that we had. Okay. And then we'll wind up writing the equation. So this is called the point slope form of a line. You've used it probably a lot. Okay, and if you know how to do equations of lines another way, that's fine. So we'd have y minus a negative 1 equals negative 1/3 x minus a negative 3. Okay, so that's y plus 1, negative 1/3 x plus 3. I'm going to go ahead and distribute the 1/3, negative 1/3, which would give me a negative 1/3 x minus 1. And then I'm just going to move the 1 out of the way, and I'll have y equals negative 1/3 x minus 2. So that's the answer to part B. This is the answer to part A. Okay. And then C was just doing the graph together with that. So let me just move over just a little bit, and I'll do part C. Okay. So the graph of y equals 3 over x, you could just use a graphing calculator, or don't forget about Desmos. It's a free graphing calculator. Real easy to use. You get something that looks like this. And then what happens is over here at negative 3, okay, you'd have that point negative 3, negative 1, and the tangent line would have been doing this, okay, where it crosses right here at negative 2, has a slope of negative 1/3. Okay. All right, so in the early part of 3.1, you're taking limits that we learned how to do in chapter 2, and you're learning that these can be used to determine the slope of a tangent line to a curve. Okay, but you're in the beginning, you're always doing the slope of the tangent line at a particular spot. Okay, so that was number 9. All right, I thought I'd also look at, let's look at number 11. Now, number 11 is doing the same thing, but it asks us to use the other formula. So I wanted to show you that. So this is another example. This is number 11. Okay. All right, so with 11, it says to find the slope, and it wants us to use this version. And remember that A in there instead of the X can look weird when you're doing it, but it's really just like having an X right there. It's just that you're going to be finding the slope at a particular point. So you're using that to find the slope of the line tangent to the graph of f at some particular point P. So here's the function they gave us. Here's the point we're supposed to find the slope at. Ooh, that's not the one I wanted to use. Let me change that. That's not hard enough. You can do that one. This is the one. X squared plus 2. And the point is 527. Okay. 527. Okay, so we want to know the slope of the tangent line to this function at x. This right here is at x equal 5. Okay, or a equal 5. They're using a when they get to a specific point. They're leaving x for later when we're doing things in general. Okay, and then this right here would be the value of the function at a. So notice if you plug in 5 here, you'd get 25 plus 2. That's where the 27 would have come from. All right, so we're just going to use, still finding the slope of the tangent line, just using the other variation that we could do. Okay, so the slope of the tangent line at an a of 5 would be given by this. We look for the limit as h approaches 0 of f of 5 plus h minus, now f of 5 we already know because it's right here, minus 27 over the h, okay? And then you're dealing with a function, so you've got to go back and look at how to do f of 5 plus h by looking back at your function, and you're supposed to take the input and square it and add 2. Still not dealing with the limit yet, so don't forget to write that. Don't get lazy. Write that. But we're going to just work on plugging in for this part right here. So that's going to be 5 plus h squared, okay, plus 2. That's that box. Then I'm going to have minus the 27 still over the h, okay? Now, a lot of your work is going to be involved in simplifying expressions that look like this. So now I'm going to just work on simplifying a little bit, okay? So 5 plus h squared, remember that's 5 plus h times 5 plus h. Don't shortcut it. Don't do the mistake of just squaring the 5 and squaring the h. It's really 25 plus 5h plus another 5h plus h squared. So this part right here is going to turn into 25 plus 10h plus h squared. Then notice we have plus 2 minus 27, so those would combine to be minus 25. All right, now notice that the 25 and the negative 25 cancels, and that we have h's in the other expression, so we can knock out one h from each of these. So h would go into h once, it would go into h squared h times. Okay, now that's what gives us finally the end result. Okay, so let me back up a little bit and not give you bad habits. So before we cancel the h, we've actually got this as simplified as we can, okay? So here's the simplified expression that we're trying to do the limit of. 10h plus h squared over h. Then dividing the h into each would give us the limit as h approaches 0. When we knock out the h from the first term, we get 10. Knock out the h from the h squared, we get h. Now we're going to actually evaluate the limit. So now we're going to actually take and plug in a 0 for the h. And then we get the answer. So the limit is 10. And that is the limit of the function of that when we plugged into that formula. It's a limit as h approaches 0. But remember, really, it's giving us the slope of the tangent line at a of 5. Okay, so we're supposed to take that slope now. This is part A. This is part B. We're supposed to take that slope value together with the point that they gave us and write the equation of the line. So that part you'll get really used to. So it's y minus 27, y minus 27 equals 10 times x minus 5. Then you just clean that up a little bit. So you distribute, add the 27. So what's that? That's 23 negative. So it'll be y equals 10x minus 23. So that's the equation of the tangent line. Okay. So that's what they wanted on number 11. So it's just a different formula. That one kind of is close to the formal definition of what a derivative really is. Okay. All right, let's do one more that has a radical in it. Let's look at number 12. Okay. So that you get practice with the 3 types. Okay, on number 12, 12 gives you f of x equaling the square root of 3x plus 1. Okay. And then they give you the fact that a equals 5. And your job is to find f prime of a, okay? So in other words, find f prime of 5. So part A is that, and then after we get that, we're supposed to get the equation of the tangent line at A. Tangent to F at x equals A. Okay, so for our purposes, we're doing f prime of 5, and we're doing the equation of the tangent line to F at x equal 5. All right, so let me go ahead and kind of transition you for a moment into 3-2. So we're not quite there, but we're going to be moving there. So when well, I'll hold off. I'll do one more just this straight way. So you have a choice about which way you want to do this. So you could set it up thinking about the first example formula or the second example formula. So let's say you decided you wanted to do this. If you wanted to do f prime of 5, well, that would equal the limit as x approaches 5 of f of x minus f of 5 over x minus 5, okay? So f of x is square root of 3x plus 1. F of 5, this particular problem didn't give you the whole point, so you need to do that. So f of 5 would equal the square root of 3 times 5 plus 1. So that's 16 underneath there, so you'd have a 4. So it's minus 4 all over the x minus 5, okay? All right, so now, whenever you have radicals, this is the time when you might have to rationalize, because the issue is if I plug a 5 in right now, I just get a 0 on top and a 0 on the bottom, and it looks like this is just not something you can do. So this is one of the algebraic techniques you should have learned from the earlier chapter for dealing with limits, is that you could multiply by the conjugate. So let me do that. Top and bottom, and don't multiply out what you have on the bottom. Just let it sit there. Okay, then when you multiply this times this, you're going to get 3x plus 1. Okay, when you do the outside 2, you're going to get 4 times the square root of 3x plus 1. When you do the inside 2, you're going to get negative 4 times the square root of 3x plus 1. Notice those go away. Okay. And then the negative 4 times the positive 4 would be minus 16. So those are gone. Down here, you're not doing anything with the denominator. You're just keeping it all in there for now. Okay. And don't forget, we still haven't done the limit part of this. So we'll do the limit, but not yet. We've got to do some more simplifying. Okay, so one of the things we noticed is these go away. Okay, these can be put together. And so on top, we have 3x minus 15. On the bottom, we have this x minus 5. And then this kind of long expression here that we got after we rationalized. All right, so notice on top, that right there can be factored into 3 times x minus 5. See that? Then that x minus 5 that was causing the problem, that was causing us to get a 0 when we plugged in the 5, we could eliminate that because we're not going to ever be at 5. So it'd be okay to get rid of that. Okay, then what we've got is that the limit as x approaches 5 would be equal the same. Doing the limit of what I had would be the same as doing the limit as x approaches 5 of 3 over that square root of 3x plus 1 plus 4. We're just simplifying that expression so that we've got something equivalent to what we had before, but now we don't have the problem when we go to plug in the 5. So now we can use the direct substitution, and we'll plug in the 5. Now the limit as x approaches 5 is gone. Now I'm doing the direct substitution. The limit notation is gone. This is the limit. Now I'm just working on simplifying it. So it's 3. This would be 16. Square root of 16 is 4. And 4 plus 4 would be 8. So the answer to the limit as x approaches 5 would be 3/8. That's what f prime at 5 is equal to. And this f prime notation, okay, is really telling me the slope of the tangent line at x equals 5 is 3/8. So now we want the equation. So what we do is we take, this is our slope. Then we take the x equal 5, but we plug it into that original function like we did earlier, and we get 4 for the y. And then we go and we do our equation. Y minus 4 equals 3/8 x minus 5. Okay, so that would be 3/8 x minus 15/8. You can use a calculator to do fractions, so don't let them make you think it's complicated. Add 4. And when you add 4 there, you really are adding 32/8. So that would be, let's see, 17. So 3/8 x plus 17/8. Okay. So f prime of a particular point is what we were doing. The derivative at a particular spot is what we were doing in 3.1. And the derivative for a particular type of function, like this one right here, would have looked like this. Let's see, it would have been -1/3. It would have been something to this effect. Okay. And then we're getting the slope of the line tangent to that at x equal 5, so somewhere out here, and we're trying to get this right here. And that slope represents, the slope at that point is like the instantaneous rate of change at that spot. Okay, and that's really the derivative of the function at that spot. So slope, this is a overgeneralization, but equals instantaneous rate of change, the slope of the tangent line. Let me do it different. Let me write it a little different. M tan equals instantaneous rate of change. And that equals the derivative. Okay. I'll just say it that way. Okay. All right, now I'm going to go ahead and do a little bit in 3.2. So 3.2 just keeps up with that. One of the big differences there is we start out coming up with a way to get a general formula for the derivative of a function at any point, and then you can plug into that formula to find the slope at a particular point. Okay, so because derivatives are really slope, okay, I mean, that's an overgeneralization, but because that's true, don't forget that that's a positive slope, that's a negative slope, this is a 0 slope, and this right here would be a slope that's undefined. Okay, because in 3.2, we're looking at coming up with just a formula for the slope of a curve, and then we're going to wind up using it to find the slope at various spots. Okay. All right, so let's do one of those. So I'm now going to 3.2, and just kind of a good classic one, but with some more difficult algebra. What might be one like number, let's see, what number was that? 9 over x plus 1. This is number 3. Okay, so this is 3 from 3.2's homework. All right, so you were supposed to use the limits to get the derivative function for f, and then you were supposed to evaluate it at some particular spots. So f of x on this one was equal to 9 over x plus 1. And then the various specific locations. This is not an ordered pair. This is an a of negative 1/3 and then an a of 5. So we're supposed to find, in part A, we're going to find f prime of x. Okay. And then once we do on B, we'll figure out what's f prime at negative 1/3, and then we'll do f prime at 5. That's the concept. So that was one major difference. And so the general formula for the derivative in 3.2, let me put that right here, was that the derivative of a function in general is a limit as h approaches 0 of f of x plus h. Rather than an a, we're not going to have a specific point to start with. F of x plus h minus f of x all over h. Okay. And so what happens as we simplify that is we get a formula representing the slope of the tangent line anywhere on a curve. And then if we want to know the specific slope at a particular value, then we just plug it in after the fact. So that's the biggest difference. Okay, so that's the definition there. Okay, so let's use that. So to find f prime of x, we set up the difference quotient and do the limit thing. So f prime of x would equal the limit as h approaches 0 of f of x plus h minus f of x over h. If you'll write that a few times, you'll have it down, okay? Which equals, in this case, 9 over x plus h plus 1 minus 9 over x plus 1. See how I'm not plugging in a particular value for the x. So the x's and h's are going to all be in there. Okay, all of that divided by h. All right, now the simplifying on this can be a little more difficult. So that's kind of why I picked a rational function, because it's one of the hardest ones. If you are going to be subtracting fractions, you have got to get a common denominator. So on this side, you're going to have to multiply by x plus h plus 1, top and bottom. Okay. And then over here, you're going to need to multiply by x plus 1, top and bottom. Okay, now don't multiply out what you see in these denominators. That's just going to be your new common denominator. It's going to be x plus h, oops, didn't mean to close it so early, plus 1 times x plus 1. Right, but we're going to do the limit of that as h goes to 0. We're going to go ahead now. Let's go ahead and take this, okay, and work that, distribute that as I go. So that would be 9x plus 9. See how I distributed there? Then this minus 9 gets distributed. So minus 9x minus 9h minus 9, okay? And then don't forget, you have all of that divided by h. But if you're taking something and you're dividing by h, that's the same as multiplying by 1 over h. So that might help save you a little bit. So if I'm dividing this whole thing by h, that's the same as multiplying by 1 over h. So that's the h right there, okay? It's dividing by h is the same as multiplying by 1 over h. So you might want to do that. All right, now let's see what we can do. So then the 9x and the negative 9x cancel out. So does the 9 and the negative 9. So I wind up, let me see where that went. Hold on. Okay, there we go. So I wind up having a minus 9h on top. Okay. I've got the x plus h plus 1 times this x plus 1. But don't forget, you also have that h right there. And you still need to do the limit, but you're just not evaluating it yet. If you did it right now, you'd get 0, top and bottom. But see how the h's are going to cancel there? Not because I plugged in 0, but because there's an h on top and an h on the bottom. So now that becomes the limit as h approaches 0 of negative 9 over x plus h plus 1 times x plus 1. So that's the completely simplified. That's as far as you need to go, is simplifying the expression before you go and you do the direct substitution. Now you think, okay, h is going to go to 0. So this is going to go to 0. So this limit becomes negative 9 over x plus 1 quantity squared. Okay. So this is the definition of the derivative. It involves this expression right here. That's the difference quotient. So when you do the limit of that as h goes to 0, you're actually getting a formula for the derivative of the function anywhere. Okay. Now, what we had to do in part B was use that formula. This is that. Now we're down to the easy part. In part B, we just needed to use that formula and find the value of the function at the derivative of the function at negative 1/3. So basically we know f prime of x now equals negative 9 over the quantity x plus 1 squared. So if we need f prime of negative 1/3, we just have to plug in a negative 1/3. See, we've already done the formula in general, so we just plug it in, simplify that. And if we need the derivative of the function at 5, we plug in a 5. Okay, so this becomes f of 5, the derivative at 5 becomes negative 9 over 6 squared, okay, which is negative 9 over 36, which reduces to be negative 1/4. And the derivative at negative 1/3 would be negative 9, that would be 2/3, and it would get squared. So that would be 4/9, and then negative 9 divided by 4/9. You could multiply, you could use that complex fraction approach I showed you before, and you could multiply top and bottom by 9. It's a good way to get rid of a denominator. So you'd get a negative 81 over 4. Okay, so that's kind of the beginning part of 3.2, is just instead of getting the value of the derivative at a point to start with, we're just using the general difference quotient, and we're finding the value of the derivative of the function in general. And then when we need a specific point, we just plug it in. Okay. So that was problem number 3. There's several like that. So again, I did one of the harder ones, the rational ones. So you'll probably have a radical, and you'll probably have maybe something that was just quadratic or linear to do. Okay. All right, now let me go ahead and comment on a couple other things that come up in 3.2 that you need to keep in mind. If f is differentiable, then it is continuous. In other words, if you already know that a function is differentiable, then you know it is continuous. Okay? You don't know this the other way around. If f is continuous, that's not enough for it to be differentiable everywhere. It may not be differentiable. And you can think, if you can think of it more specifically, if f is differentiable at a spot, then it is continuous at that spot. If f is continuous at some spot, it may not be differentiable at that spot. And here's my example, my counterexample, that right there. And the reason that's not differentiable is the slope of the tangent line to the curve at that spot, you can't say what it is. It looks like it's this, and then it looks like it's that. It's not the same thing, okay? So there's a continuous function that's not differentiable. Remember how these sharp spots right here, that's one of the things that causes a problem, that causes something to not be differentiable. So does having the limit not exist. So like if you have a function doing something like this, and then this, okay, then the limit doesn't exist at that spot, so it wouldn't be differentiable, okay? So if f is differentiable, then it is going to be continuous for sure. But if f is continuous, that's not enough to say that it's differentiable, because you might have something like an absolute value function in that sharp point. At that sharp point, it would not be. Okay, so let me go ahead and go to one of those where it asks you to try to take a function and graph what its derivative would be. Okay, so let's look at one like number 13. So this is good just for thinking about slopes. So number 13 says, use the graph and, okay, yeah, use the graph. And on part A, it's asking you, where is it not continuous? On B, it's asking you, where is it not differentiable? And on C, it's asking you to sketch the graph. Okay. All right, so let me try to reproduce the graph, the original graph. So the original graph looks like this. Okay. Okay, so it does something like that. And then mine has a little open circle right there. And then it's got a closed circle right here. And it goes down here to about right there. And it crosses on the inside. So it does something like that. It's nice and smooth though. Then it winds up picking up from there and just going to about right. Oops, dropped my pen again. Trying to even up my scale here a little bit. Going to about right there. Okay. Does something like that. Okay. Now you really need a really pretty decent picture to get a very good graph. But if you're doing multiple choice options, this might be good enough. Okay. So this is f. It's not defined by a rule. Okay. It's not defined by an equation, so we can't use any algebraic technique to do it. All right. And so you can tell there's some interesting spots at 2 and at 3. This is 2, 4, 6. Okay. And so it says on the interval from 0 to 5. So we're looking on this interval, not including the endpoints. Where is it not continuous? So you see it's not continuous only at an x of 2. But it's not differentiable there because the limit wouldn't exist at 2, but it's also not differentiable at 3 because of that cusp. They call that a cusp, that sharp point. So the tangent line looks like it would be different. It's hard to determine the tangent line based on which side you're at. All right, now when you go to sketch the graph of the slope, I like to do that kind of right below the other one. So I'm using the same scale, trying to line things up for you. Okay, draw that better. These are going to be important spots right there. Okay, so let's think about that. So notice on this piece right here, the graph is rising, so the slope is positive. Here it's falling. Oops, said falling and I wrote a positive. Falling, so it's negative. Here it's positive. And you can't tell, you can't see it so good from where you are, but I can see it on mine, that this one being a straight line, I can count up and over, you know, and it looks like it goes up 6 while it goes over 1, 2. So it's going up from -1 to 5. So that would be up 6 units while it goes over 2. So the scale is hard to read, but that's what it appears to be. So the slope of this is positive, and I know it's a positive 3. Okay. So for instance, when I go to think about what the graph of this would look like, between 3 and 5, I'm going to have a slope that's positive 3. So this is 2, 4, 6. So slope of positive 3 from 3 to 5. So it's going to look like that. Okay. But at 3, I'm going to have an open circle. Open at 5 as well, by the way. Well, it could be open, or you could just have it end like that, because we don't really know what's going on there. Okay, now between 2 and 3, the slope is negative. So we have to be down here. We have to be below the x-axis. And look at how the tangent lines, I always use these little mini tangent lines in my mind. So see how that has a negative slope, kind of shallow though, small number, but then it gets steeper, 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 more and more negative. So that means that's going to be a line that's negative, but with a small number part to start with, and then it's going to get more and more negative. So it's hard to put it exactly where it needs to be, but it is going to be negative and getting more and more negative. And you know, it's almost horizontal right there. So I'm going to draw it as like, just, it looks like it's almost right at 2. Maybe a circle at 2. Let me do that in red. And then it gets more and more negative. Okay, so maybe something like that. Okay. And then an open circle on the other end of that. Okay, and then the one in the beginning, it's not a horizontal line because the slope of that, these two right here are not horizontal because the slopes are not of lines. So the slope is not constant. Here starts off not so big and then gets more and more, the tangent lines get steeper, 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 okay? So this one would be one that's increasing, but you know, it doesn't get all that steep. So I would say that one would look maybe something like this. Okay. Okay. All right. So again, it's kind of hard to, and I'm not saying that the slope is 2 at that spot. You know, these curved ones, I can't really specify specifically how that looks. Ooh, and that should have gone all the way. It should have gone all the way to here. Something like that. Okay. All right, so that's the gist of it. Now, these will usually be multiple choice since you can't really determine the what these would look like without having an equation where you could actually find the derivative. So you wind up just looking at the multiple choice one that fits what you see as good as you can get it to fit. All right, so a couple other things we talked about then in section 3.2 is the idea that if your function is differentiable, then that implies it had to have been continuous. It must be continuous. But watch it. A function can be continuous, but it may not be differentiable. And that's because you could have a sharp point like that. All right, so that's what's going on in section 3.2. is you're working with coming up with a general formula for the derivative. Okay. And once you get that general formula as simple as possible, which is right here, okay, with the expression as simple as possible, you use direct substitution and think about h approaching 0. And what you wind up with for your answer right there is a general formula representing the derivative of your original function at any location. So then if they ask you to find, well, what's the derivative at negative 1/3? What's the derivative at 5? You can find it, okay? And the derivative at negative 1/3, when we say that turns out to be negative 81/4, remember that's the slope of the tangent line to the curve at that spot. This is the slope of the tangent line to the curve at that spot. So keep in mind, have that association that derivatives are really just slopes. And that way, when they ask questions, you'll have a sense of how to approach them. Because sometimes they ask you for like the equation of a tangent line rather than just the derivative. All right, I'm going to stop this video. Then I'm going to make some with the shortcut rules we're learning beginning in section 3.3.